in person. You know, once upon a time, about a year ago, they said, all right, after Thanksgiving, everything's on Zoom because we don't want everybody going off, Lord knows well where, getting COVID, coming back and having a super spreader event. I'm not sure if that was ever really a problem, or if it was a problem, it's not nearly as much of a problem now. Because what was I going to say? I was going to say, I don't remember, but no, we're meeting. We're meeting. That's I was going to do this. I was going to stop the share so that I could pin my video, so that I could do this, and then I could do this so that mine is the only one showing. Maybe there it is. All right. Okay, so now I don't have to worry about some random name showing up there. Okay, but no, after Thanksgiving we will resume. And I was trying to think about what are we going to do between now and the end of the semester. There's a chance that we're going to finish chapter 9 today. I'm not going to rush it. If it happens, it happens. If it doesn't, it doesn't. But something else dawned on me earlier today as I was grading my Stats 1 tests. You guys took a test and I hadn't graded it yet. They got stuck in my bag and I'd forgotten that y'all had taken it, or that y'all had taken it and I hadn't graded it yet. So I'm sorry, but at the same time, I'm wondering why nobody said, hey, what's my test 2 grade? So it was a while back, was last Monday. Yeah, and you know, and then I was like, okay. Then I was digging through my stuff, and I was like, what's this? Oh, there's y'all's test. So, and they got. Well, have you ever stuck something in a pile and forgot it was there? Oh, hush. I gave you opportunities to get bonus points. By the way, thanks those of you who came to the math talk last Thursday at TJC. Actually, I had more UT students show up than TJC students. It was kind of disappointing. It was impressive from the UT side and disappointing from my side. There were a lot of students there. There were about 125 people in attendance, which was, I was like, good. And the guy was really fascinating. He talked for an hour, but I mean, the stuff he talked about using statistics to predict when the next big terrorist event would come up. And he was right. Or using statistics to modify people's behavior. Like, and I can't get into all the details, but it went something like this. Well, we measure these 62 characteristics of people that might do terrorist events, and the same 62 characteristics of people that get online onto aljazeera.com and rant about blowing things up, but not. And we realize that out of these 62 characteristics, if you just focus on these 3, you can turn somebody from blowing up a building to just writing about blowing up a building. And so the government would focus on that because he's done a lot of work for government. He's done math on that. And I understand this math, that if you're tracking somebody shooting at you, the minute they shoot at you, like with a rocket launcher or something, you can instantly calculate their location based on the trajectory of the rocket and immediately retaliate. Or you could measure sound waves and then determine what type of vehicle there is, you know, a couple 100 miles away with like 98% accuracy. It was crazy, the stuff he was doing. But the most impressive thing about his talk is that afterwards, about 30 students hung around and asked him questions for about half an hour. I was like, wow, normally it's over, everybody runs. But it was pretty fascinating, and I wish I had recorded it, but we hadn't made the arrangements. So, oh well. But it was a pretty interesting conversation. All right, but anyway, so by the way, I remember now that you have a test that I haven't graded, so that is on the forefront of my radar. Aside from that, does anybody have any questions they'd like to ask, homework problems they'd like to look at? Because I do believe I gave an assignment. I did. It was here. Hold on. I know where that is. There it is. This is the PDF from the Zoom session last time, and somewhere on the bottom of it was a homework assignment. There it is. Quiz will be available soon. Now the quiz over 2.5 and 2.6 I did write after the Zoom session on Monday, and I forgot the due date that I put on it. I think it was this Friday. Okay, and I also learned something else about Canvas, which I'll tell you in a minute. I haven't yet created the quiz over I can't highlight this because it's just a PDF. I haven't yet created the quiz over the homework from section 9.2. or 9.1, excuse me, that's 9.1 homework. So be on the lookout for that quiz. It will eventually show up. I got bigger fish to fry like grading test right now. But does anybody have any questions they'd like to ask about? I do. Where the heck is everybody? 1, 2, 3, 4, 5, 6, 7. Well, I'm one of them. 8, 9, 10, 11. Okay, that's a good chunk of them. Welcome, Andres, Colton, Jeffrey, and Taylor. And I knew some of those were going to be on there, and some of them just show up on there, but that's okay. This is being recorded, so it'll be made available later, as will the notes from the whiteboard. So hopefully those will help you out. All right. But yeah, I was thinking about, what are we going to do to wrap things up? We're definitely going to finish chapter 9. We may finish it today. If we don't finish it today, we'll finish it Monday. I think what I'm shooting for is to really just do the first section of chapter 10 justice. Because the first section of chapter 10 is when we start talking about regressions, lines of best fit, but with multiple explanatory variables. So instead of saying like, let's predict the amount of calories in a cereal based on how much sugar it has, we could say, let's predict the amount of calories in a cereal based on how much sugar, how much fat, how much whatever, and we can rattle off as many explanatory variables as we want, and we're not limited to a simple regression, but we got to get through chapter 9 before we get there. Okay, so does anybody have any other questions or comments before we begin? He doesn't. I've looked. A lot of the stuff he was talking about, he couldn't disclose information, because he's done work for the NSA and for the CIA and a lot of military intelligence work. So sometimes he spoke in generalities, which was frustrating. Sometimes he would actually work on something and all the government would do is give him the data and not tell him what it measured. And then he would give the results back to them and have no idea what those results meant, because, it's on a need to know basis and he didn't need to know. So I thought that was real, spy James Bondish. Although I did learn something, that in the CIA, in their commissary where they eat, they only have one news channel on the monitors. And he said, guess which news channel it was. Come by afterwards if you want to know the answer. And some people correctly guess. Anybody want to guess what the one news channel they watch in the CIA is? Nope. Fox. I was like, wow, I wonder way to do that. Is everybody in the CIA right-leaning, or do they just believe that? I don't know. I'm just speculating here. Maybe they lost. That's it. They lost their Central Intelligence Agency can pinpoint your location down to the nearest foot from anywhere on the globe. Can't change the channel on TV. Well, it's like changing the clock the clock on your radio in your car when the time changed. I'll just wait 6 months. It'll be right then. All right. Okay. So let's begin. All right. Let's see. So what is today? Today is Wednesday. Yes. November the 10th. Yes, it is. Tomorrow is Veterans Day. Any veterans? Thank them for me. Wednesday, November 10th. This is Math 1343-001, which is the only section of Math 1343 this semester. Most of the time, there is only one section of Stats 2. And when there is, I usually get to teach it. And of course, this is UT Tyler. All right, so if nobody has any questions, then we are just going to continue by looking at 9.2. All right, so last time we barely scratched the surface on 9.2, and I think I closed the PDF. I did. Let me go back and open that PDF again. Modules. It's the very last one in Zoom. There it is. All right. I just want to remind everybody what we did, or rather did not do, from 9.2, which is at the conclusion of this. We talked about ANOVA for regression in a very small capacity. I left out an E here. Test the effectiveness of the simple linear model. And we explore the variability. And I remember bringing up the pages in the book and pointing out some things, but we do an ANOVA table, and the null hypothesis will always be the model is ineffective. And the alternative hypothesis will always be the model is effective. So we're just going to jump right into a problem and see what happens, and then I'll document all the things that you need to know how to do. All right. So I'm going to fast forward through the end of section 9.2. We're going to do an ANOVA problem. And a lot of this is going to be really, really quick and easy because it's just say, hey, look at the computer output. And what does this mean? Not a whole lot of calculations, although I will ask you to calculate some ANOVA tables in a little bit. And I got to remember there is one other formula. It's that one that we're going to need because we'll need that for 9.3. And if I forget it, then when we get to 9.3, I'll say, hey, I forgot this formula, and we'll go back and get it. It's a real easy formula. What it means is a different story. I mean, it looks like a mess, but really it's like, here's the big formula, but it cleans up to that and it cleans up even more. So the formula is eventually going to be take the square root of MSE once you get it out of the ANOVA table. So it's not a complicated formula. It's just one that we're going to need at some point in time. Okay, so let's just jump into a problem and see what happens. Let's look at some of these first questions. We have an ANOVA table for regression, state the hypotheses, give the F statistic and p-value, state the conclusion of the test. Now, when you're asked to state the hypotheses for an ANOVA for regression, they will always be the same. It's what I just showed you, and I think I'm going to start the whiteboard discussion with that. Okay, so let's begin the math. 9.2 ANOVA for regression. And the goal for ANOVA for regression is to test the effectiveness of a linear regression. This is equivalent to asking how good does the explanatory variable predict the response variable. Now, it's never going to be 100% effective because unless there literally is only one thing affecting the outcome of something, then there will always be things that are not accounted for. And so we'll never hit 100% effectiveness, so to speak. Now, when you do this, it will be a hypothesis test, and the null hypothesis will always be the model is ineffective, which sounds a little bit contradictory. If we break down the math, you would see why it has to be that. So the null hypothesis will always be the model is ineffective. Now, there's a couple of equivalent ways to say this, or you could say the predictor is ineffective. When I say the predictor, what I'm really saying is the explanatory variable. How well does the bill amount predict what the tip's going to be? So the predictor is the bill. And I know that there are other variations of the model is ineffective, but we'll just run with those two for now. And so then what happened there? Oh, I know what happened there. Go away. You bother me. All right. If the null is the model is ineffective, guess what the alternative is? Model is effective. I had somebody tell me once the model is not ineffective. You're not wrong, but it's better to say the model is effective. And of course, the other version would be the predictor is effective. The predictor is effective. So just looking at what? Oh, well, you wouldn't tell just by looking at a scatter plot. You would tell by looking at the computer output. Because what the computer output does is it takes all these ordered pairs and it cranks out an ANOVA table or regression output or some other things. But the way that we're going to do this is we're simply going to look at the p-value. If the p-value for the model is too small, and when we're not given a significance level, do you remember what we assume? Yep, less than 5%. Or whatever significance level is given. Well, what do we say when the p-value is too small in terms of a decision? Reject the null. And we reject the null hypothesis. But since the null hypothesis is always going to be the same, we can be a little more specific. In other words, If the p-value is too small, then what does that say about the model? Then the model is effective. The null hypothesis is saying, nah, you don't predict this. And then we see a sample that does something. The p-value is the probability we would have seen that sample if the null hypothesis were true. So if your p-value is too small, then the probability we would have witnessed what we witnessed was so small that we shouldn't have seen it if the null hypothesis was correct. Conclusion, null hypothesis must have been wrong. We reject it, and therefore the model is effective. So some of these problems end before they begin, especially if they give you the p-value. So like I said, there's almost no work on these, and it is 100% observation and interpreting the results. So let's go look at some of the questions in the homework. We'll look at the odd ones because I need to save something for your quiz. All right, so again, the instructions on this first batch are to state the hypotheses. Well, guess what? They're going to be the same every single time, unless you get context specific. For example, instead of saying the model is ineffective, I could say the bill does not effectively predict the tip. And the alternative would be the bill effectively predicts the tip, or whatever your explanatory and response are. So you can phrase the hypotheses in context, but it will always be the explanatory variable does not effectively predict the response variable for the null, and the explanatory variable effectively predicts the response variable for the alternative. All right, so let's take a look at some of these. Give the F statistic, the p-value, state the conclusion. We'll look at number 31, and I'll zoom in as much as I can to keep it on the screen. If somebody walked in here and I just asked them what's the value of the F statistic, where do you think they would go? Right, where's his F? I mean, you have to know what that means. Well, I guess you want this number and you would be correct. So the value of the F statistic, that's actually your test statistic in the hypothesis test, but more importantly is that they give you its p-value. And remember, the p-value represents the probability we would have saw that sample. If we drew the picture, the p-value would be the area of the tail that the test statistic cuts off. In other words, if we were actually doing a full-blown hypothesis test from beginning to end, and we had a F statistic, which is a right tail test, then we would have F equals 21.85. Can y'all see that? Okay, I know the thickness of the line is pretty fat, but that's because I'm zoomed in so much. This would be our test statistic. And the p-value would represent the area of the tail cut off by the test statistic, but it also represents as a probability, the probability we witnessed the sample under the assumption the null hypothesis was correct. But that's, to 3 significant digits, there was a 0% chance that we saw what we saw. Well, if something has a 0% chance of happening, when can you expect it to occur? Never. So if the null hypothesis was correct, we had a 0% chance of seeing what we saw. Well, we saw what we saw, so the null hypothesis must not have been correct. So again, these ANOVA problems, when you're given this table, are over before they begin. P-value, less than 5%, reject the null. Next question, please. Woohoo, yay for easy. Okay, so does anybody have any questions about why we reject the null hypothesis there? I don't know what else to say about it. It's over. We did it. Now we could answer the other ones real quick. Oh, look at that p-value. Would we reject the null hypothesis there on number 30? No, it's not less than 5%. What about this one? I'm not sure what's up with this double asterisk here. A response, why? Okay, so they're being generic here. The response value is the Y variable. And I'll admit that in some of the computer outputs, they'll say one thing or another, but the content is pretty much the same. Look at this ANOVA table. And we can look at the other stuff in the ANOVA table, which we will do in a moment. But these first few questions are, I want to say they're insultingly easy. And if you couldn't do them, then I guess that would be justification to say, man, y'all are stupid. and for the recording and for those who are on Zoom, this is an allusion to something we discussed before class. Yes, sir. As a percent, it is 18%. And I wouldn't call it wrong if you said 18%. I wouldn't call it wrong if you said 0.187. You know, if you're going to call it a percent, I would rather you call it 18.7%. But yeah, you can refer to the p-value as percent and state the conclusion of the test. Yeah. Fine, round it off 19%, but you know, why, you know, if it's only, I'm not asking you to do math, I'm asking you to write the number down. So, but yeah, I know it's hard to write that third digit. Math is hard. All right. Okay. So any questions about looking at the results of an ANOVA table and knowing where to go to make your decision? Yeah, it's a little bit easy. Oh, there's another one over there. How nice. Now, I will say that sometimes the notations they use are a little bit weird. Like if you look on number 33, and it's the same thing on number 32, above the p-value, it doesn't say p. It's got this mess. It's got this mess. What the heck is that? Well, that's the probability that you sample that you see has a greater test statistic than this. So, but it's just p-value. It's just a messed up way of saying it. And as a theoretical mathematician, this notation that's currently highlighted absolutely drives me crazy, because when you see a greater than sign, you should see something on both sides of it, and there's nothing on the right side of this greater than sign inside the parentheses. So that just makes me just want to hit whoever says that's a good idea. So don't say that's a good idea, because I don't want to hit you. All right, so p-value by any name is still a p-value. Okay, let's see what else we have here. Oh, what's this? Calculate R squared. We need a formula. Now, we had talked about the coefficient of determination before, and I want to go back and remind you what that was in the PDF from the Zoom session last time. When we talked about R squared, it was the coefficient of determination. And let me zoom in on this a little bit more. But the R squared, the coefficient of determination, measures the proportion of variability in the response variable that can be attributed to the variability in the explanatory variable. Well, that is so bad. Explanatory. That's awesome. Here it's supposed to say explanatory. So when you interpret a coefficient of determination, when you interpret R squared, you can pretty much say the sentence that's highlighted in yellow, but the things highlighted in pink would change based on the context. Some percent of variability in the response variable can be attributed to variability in the explanatory variable. I think this needs to get documented in the whiteboard for the current Zoom session. So let's go over here and make some comments about that. The coefficient of determination. Something didn't feel right when I typed it. I know that sounds weird, but when I'm typing, if I mistype something, I feel it. I don't know. The coefficient of determination, which is R squared, it can be lowercase r, measures the percent of variability in the response variable that can be attributed to the explanatory variable. It's almost like asking, all right, what percent of this change can I blame on you? It's not really a blame game, but it's like, it kind of is. Now, the only other thing that's missing is, where do you get this R squared from? And the formula for R squared, the formula for coefficient of determination, is actually pretty straightforward. It's SS model over SS total. And it's worth pointing out that these two things, I'm going to type this part. It's worth pointing out that these two things, these come from the ANOVA table or the regression. Not the NOVA table, that's a car. These come from the ANOVA table for regression. So it's a really easy something to calculate if the ANOVA table is given to you. So let's take a look at a problem where the ANOVA table is given to you. If we can get back to this, I want the book, and the book is here. All right. So use the ANOVA tables from the previous problems to calculate R squared and to give the sample size. All right, we'll talk about the sample size in a minute, but let's go back to number 31. And let's see if we can figure out where to find the numbers that will create the coefficient of determination R squared. All right, it's SS model over SS total. Now the SS total is pretty transparent, at least I think it is. Do y'all see where in this ANOVA table the SS total is? Yeah, it should be pretty obvious. It's right here under the SS column in the total row. But where's SS model? It's the top one. There are a lot of synonymous words that are tossed around in this context: model, regression, explanatory variable, et cetera, et cetera, et cetera. So it's worth mentioning that SS model could also be called SS regression, but it's not SS error. The error one is usually pretty obvious because you see the word error is in the second row. So using those two numbers, and I'm just going to take a picture of them real quick so I'll know what they are when I leave this screen. And there they are. Hello. There it is. Okay. So in number 31, so for example, let's bump the font size back up. It's not time yet. Question 9.31. We have SS model is equal to 3396.8. We have SS total is 30,450.5. So the coefficient of determination R squared is just the first number, 3396.8, divided by the second number, 30,450.5. And we'll round it to what, 4 decimal places. Sounds good. So what's that equal? Yes, sir. I usually lowercase it, but sometimes I capitalize it. And in this case, I'm super inconsistent because every time I typed it, I changed the case. It doesn't really matter. If you look in the book, most of the time, I believe it actually has a lowercase r, but I could be wrong. Maybe one Locke family member said capital R and another Locke family member said lowercase r. But in this case, they mean the same thing, which is crazy because I know a formula where they mean different things, but in business math, where lowercase r represents interest rate, but uppercase R represents regular periodic payment, excuse me. But yeah, for our purposes, if I say lower or uppercase R, they pretty much mean the same thing. And I'm glad you asked about that because I'm being as inconsistent as you can be right now. All right, but the answer to the division problem to 4 decimal places is 0.1107. Or if you wanted to write it as a percent. Apparently, I'm going to guess that that's not the correct answer because of all the rumblings going on. I very easily could have mistyped it. It would not be the first time. But I'm also happy that you caught it so quickly instead of just letting it sit there and fester. How about 11.16? Is that better? Okay. It wasn't off by that much. I think when I typed the top number, I got the 9 and the 6 switched up. Okay. Rounds off to 11.16%. So if this had context to it, we would say that 11.16% of variability in the response variable can be attributed to the explanatory variable. Or in other words, the explanatory variable is 11.16% responsible for how the response variable changes. Gee, I wonder what the other 88.84% is attributed to. Oh, good question. All right, so any questions about calculating the coefficient of determination from an ANOVA table? Okay, it's pretty straightforward. Now, there was a second question in this part, and I'm not sure if you caught on to it because I kind of glossed over it. Let me go back to the question and show you. And I want to remind you that the whiteboard will be saved as a PDF. So if for some reason you missed something, you'll be able to pick it up later. All right, so let's go back to the actual statement of the question, which was over here. We calculated R squared, but there was something else that they asked us to do. Sample size. All right, so if we want the sample size, then we need to know a little bit more about how the ANOVA table was built. I'm going to show you this, but I'm going to write it in the notes as well. So let's go back to where the ANOVA table has all its formulas, and it's out there for the world to see. It's up here somewhere. Yep, they use capital R there. Let's see. And if you're wondering, what about all this stuff we're skipping over? I'm skipping over it for a reason, because we're not going to talk about every little nook and cranny. All right, here's the ANOVA table. And if you compare it to the ANOVA table from your last test, you'll notice that it's real similar in some aspects. The way you calculate the MSs is you take the SS and you divide it by whatever the degrees of freedom was. And I think we talked about why this is always one. There's well, it's not that there's two variables, it's that there's one explanatory variable. So that's really just measuring the number of explanatory variables. Actually, it is 2 minus 1. It's k minus 1, where k is the number of variables, but it's always going to be 2 in a simple regression, 1 explanatory, 1 response, and then 2 minus 1, of course, is 1. Yes, I remember having this discussion now that in the previous ANOVA table, it was k minus 1 here, and it was n minus k there, and then n minus 1 at the beginning. In ANOVA previously, k was the number of populations we were testing simultaneously. In this context, k is the number of variables in our regression equation. But if it's a simple regression, there's 1 explanatory, 1 response. So for a simple regression, k is always equal to 2, which means k minus 1 is equal to 1, and n minus k is the same as n minus 2. Now, later, it is going to say k minus 1 and n minus k when we have more variables. But for now, k is 2, so it collapses down to that. But the question that was being asked is, what's the sample size? And we can recover it from a couple of different places, but the easiest place to recover it is down here, because our total degrees of freedom is just sample size minus 1. So if we were looking at an ANOVA table, and that's not it. If we were looking at, where did it go? Oh, in this PDF, I just got to scroll back. So if we're looking at an ANOVA table and the question is, what's the sample size? We just have to go look at the total degrees of freedom and not use that number, but do something with it. So let's go back to number 31 for a second. All right, so there's number 31. One more zoom in. There it is. Anybody know the sample size? 176. Because this is not the sample size, but rather this is the sample size minus 1. And if we did just a little bit of baby algebra and added 1 to both sides, we would get that the sample size is 176. But just be careful, because the sample size is 1 more than the total degrees of freedom. Now, I'm going to summarize this in the notes, but before I do that, does anybody have any questions about why the sample size is 176? All right, so let's summarize that in the notes. Okay, I need another page. If you need that back, I'll put it back in just a second. To find the sample size from the ANOVA table, observe that DF total is equal to n minus 1. So our sample size is just degrees of freedom for the total plus 1. We don't even need that formula, but if you want one that says n equals, that's what it would be. All right. Was there something on the previous part that I needed to go back to? Because I switched over and I sensed a disturbance in the force. So we're okay. All right, so that's pretty easy. All right, let's go back to the book. Zoom out, go find some more stuff to do. All right, what are we doing? In the next exercise, we give some information about SS's and a sample for a linear model. Uses, all right, now it's time to fill in the ANOVA table. All right, this isn't that bad. Now, well, it's not that bad, and then it gets kind of crazy at the end when we're asked the p-value. So we're going to talk about how to dig a p-value out. And I think we might have talked about this in a little bit of capacity, but there's got to be a better way to do it. Let me grab number 39. Let me grab it out of here, and I will move it on over to turn that off. Grab this, and I'm going to put this inside of the whiteboard. So give me a second to copy it and switch over to the whiteboard. And if you're writing it down, don't worry. You're about to see it in just a second. New page, please. Thank you. All right. Now let me preface this with the instructions. Use the following info following. Use the following info to construct an ANOVA table. Remember, all this is about regression. So we've got everything that we need, ideally. On your test, when I ask you to complete an ANOVA table, it will already be drawn out for you. But since it's not done here, I'm going to go ahead and draw it out myself. We have model. I'm not sure what happened to the front end of that M. This must be my crappy stylus. Start doing yoga. Right here, do yoga? No? Tried it? I hear it's not only supposed to make you more flexible, but just get you in better health in general. Okay. Just need to stop making excuses. Wait, go to the gym for an hour, or they're asking them questions for an hour?
No, they were asking, okay. So like the question, one question would be, would you rather have to text an X or go to the gym for an hour? Gym. And log, no, turns out 40, like I want to say it's like 57%, because I'd rather text an X than have to go to the gym.
Okay. All right, so for those in the Zoom session who are wondering why there's a lot of silence right now, we were listening to a story about yoga and exercise and people rather texting their ex than going to a gym. And I'm not downplaying the conversation that you just had, because I thought it was pretty interesting. But, you know, for those folks on Zoom crowd, they're like, what's going on? We were having a side conversation, which is easier to have when you're here. All right. So let's start by writing the formulas. The formulas, and I'm going to write them real small because we're going to fill in the numbers. DF model, easiest formula ever, 1. DF error is n-2. And DF total is n-1, which is the sum of the first two. The SS's are usually given, but keep in mind that this column is additive. And remember, all that means is that if you add the first two, you get the third. And in fact, the first two columns are additive, but they're the only ones we can talk about being additive because they're the only columns with 3 values. So if you know 2 of them, you can find the third by completing the addition problem. And for the MS's, each MS is just the SS divided by its degrees of freedom. I'm going to move that over just a little bit. No, that's not what I meant to do. I'm going to move that over just a little bit. So that's summarizing both MSS formulas in one small package, if you will. What is going on here? I just want to draw. Okay, for the F statistic, it's just your MS model divided by your MS error. But the real question is, how the heck do we get this guy? Now that's going to be the tricky part if I ask you to complete the p-value in the ANOVA table. But this problem is actually pretty easy. We just need all the information. We have everything that we need. So let's start with the information that we were given. I think it's pretty clear where the 800 goes. Rat cheer. Not right here, rat cheer. That's redneck for right here. Yeah, put that rat cheer. Okay. I got that from Hee Haw, and if you don't know what Hee Haw is, that's my childhood. YouTube it. It's an old TV show. Well, whatever. I mean, I'm sure you can watch episodes somewhere. Where's the 5820 go? SS total. I mean, it's not rocket science, but I'm sure there is some linear regression in rocket science. All right, so that's what we were given. And we were given the 40, but you know, the 40 doesn't go directly into the table. I'm trying real hard to find a 40 joke there, but I can't find it. So what do we do with the 40? It is in. All right, so 38 here, 39 there, 1 there. That was hard, the 1. All right, okay. All right, so what about SS error? So try to get 50,020. I didn't write where it came from, but is everybody clear where that came from? We subtracted. The MSs, however, I will write the formulas, but you know, for the first one, it's so insulting to even write it. It's not really a mistake. It was inefficient. You would have gotten the correct answer, but it was an inefficient use of your keystrokes. Now, the other one, of course, that's going to take some ciphering, if you will, some figuring. Yeah, especially 800 divided by 1. But you know, the problem with typing 800 divided by 1 is if you mistype it and write the answer, that's when a professor go, man, y'all are so stupid. That's going to be a recurring joke from now throughout the rest of the semester. I have no clue what this equals. I'm 99% sure it doesn't divide evenly. Oh, thank you. Oh, wait. Oh, Jeffrey's in the class at y'all, so y'all can catch Jeffrey up on it. I thought you said something about Jeffrey having a text there. 130.1053 or 132, excuse me. I think y'all agreed with me, and I didn't even say the right answer. 132. You heard the decimal, 0.1053. Yeah, teacher said it must be right. You shouldn't. I'm human. I make mistakes. And so to figure out what the F is, we just have to divide those last two answers. So 800 divided by that decimal 132.1053. So we'll take it to 4 decimal places, 6.0558. And if you're thinking 7, I'm thinking round it. Okay. All right. So, you know, those calculations, they're pretty straightforward. There's not a whole lot of hoopla to them, but the homework question also asks you to find the p-value. Dang. How do we do that? Of course I do. Actually, I don't. I don't have a solution manual for the book. What? Now, I know how to get the F value. There's 2 ways to get the F value, using a table and using technology. Excuse me, not the F value, the P value. Well, we got the F value, but I did use technology, but push comes to shove, I could do the division problem manually. But the P value, on the other hand, the P value can either be obtained using tables or technology, sort of. This deserves its own page. To find the P value, we have 2 options. Number 1, try to use the table. Notice I said try. Now, we had an F table. It was 4 pages long. I only gave you 1 page on your last test, which I remember now that I have to grade. Let me go pull up the F table from Canvas. Go back to here, go back to here. Did I say, you know what? I probably said ANOVA, and let me go find the F table. That's what I meant to say. You know, it makes me wonder in my career of 20 plus years of teaching, how many times have I said one thing but meant another and nobody ever blinked? It's kind of scary. All right. Oh, look at this. We have 2 of them. At least I'm consistent. Haha, now we have 1. All right. F distribution. Let's download this guy because I'm going to zoom in on it a little bit, probably. All right, so we haven't seen the F distribution table in a while because we don't use it too terribly often, but it's got multiple, it's a 3-dimensional table because we have three things we have to look up: the significance level, the degrees of freedom for the numerator, which is the same as the degrees of freedom for the first degrees of freedom, which in this case is for the model, and the degrees of freedom for the denominator, which is the degrees of freedom for the error. But if we're going to try to find the p-value is the area of the tail cut off by the test statistic. So just a reminder, and I'm going to type what I just said. Try to use the F table. Recall that the p-value is the area of the tail cut off by the test statistic, which in this case is the F. So there's a visual component to finding the p-value if you draw your F distribution. All right, so we have F equals, I don't remember what it was. It was 6 something. Oh wait, it should still be my calculator, 6.0558. But we also need degrees of freedom for the numerator and degrees of freedom for the denominator. And if you are using the F table and you need these 2 degrees of freedom, they will always be the first 2 degrees of freedom here. So the 2 degrees of freedom that we need are 1 and 38. Wrong color. All right. And our p-value is this area. So all we got to do is go find the correct area in the F chart, the F table. Let's attempt to do that. I know, good luck with that. All right, so first we need to, gosh, how are we going to do this? Well, the significance level will actually kind of tell us the area. Oh, no, because significance level is an area. Remember when we do a hypothesis test, we draw the curve and we separate the regions, and the significance level is the area of the rejection region. So really what we're looking for is which of these areas is going to be our best guess for the p-value. But how the heck do we do that? Well, what's our degrees of freedom for it was 1, right? Our first degrees of freedom, and the other one was 38. All right, so let's go down to 38 and see what we see. Okay, so I'm going to highlight it. We'll highlight it in blue. All right, so that is the value of an F statistic. But what was our F statistic? 6.0558? Okay, that's not it. Okay, we're on the wrong page. Next page. 1 degree of freedom in the numerator, 38 in the denominator. What was our 6.0558? Now that's still too small. Keep going. That's closer. Still too small. Keep going. Oh no, we're on the last page. We're not going to find it exactly. But at some point, oh, look. That's too big. So what does this tell us? Well, it's somewhere between the 2 significance levels. Because with the correct degrees of freedom, when the area is 1%, the F statistic is that. But back here with the same degrees of freedom, when the area is 2.5%, the F statistic is that. So what does this mean about our p-value? Well, here's what it means. I'm going to attempt to summarize everything that I just said. And of course, I left absolutely no room for it. So I wish I could make this picture smaller. Wait a second. Hold on. I'm going to try something here. I may regret doing this. I've done this accidentally before, but this is the first time I've ever tried to do it on purpose. All right, so not too shabby, could have done worse. All right, so here's what we know. And you're like, God, it's a lot of work just for the p-value. From the F tables, we know that we have this picture. When the area is 0.25, our degrees of freedom, and I'm just going to put df equals without writing numerator and denominator. The value of the F was something, versus when we have the other picture, and I'll go back and get the values of the F in just a moment, when the area was 1%, 0.01, with the correct pairs of degrees of freedom, our F was something else. So let me go get the 2 F scores that were from those 2 pages, and I'll be right back to this in just a second. You're right. It is. That's 25%. That's just a little bit. You're right. It is 0.025. Very good catch. Told you I'm not flawless. I make mistakes. You suspect something, call me out on it. If you're right, I'll thank you for it. If you're wrong, I'll ridicule you. I wouldn't do that, at least not out loud. Okay, so when it was 2.5%, our F statistic was 5.4463. 5.4463. 5.4463. And when our area was 1%, then it was 7.3525. 7.3525. So what does this mean for what we want? Well, if you'll notice, this F score is between these two. So as the F moves to the right, the area of the tail shrinks, which means the area that we want is between 0.01 and 0.025. Now you actually don't have to write all this down, but the best you can do with the table is to get a range of values for your p-value. I don't know what my p-value is, but I know it's between those. So that's the best I can do here. Now, can we make a decision based on that? Sure we can, assuming a 5% significance level. If my p-value is between these, how does that compare to 5%? It's less than. I don't know what the p-value is, but I know because it's trapped in there, it's got to be less than 5%. This should probably be written on the next page. Since the p-value is between 0.01 and 0.025, we know it has to be less than 5%, thus reject the null. All right, so we couldn't actually get a good p-value, but we could still make a decision if the question was make a decision. But the question in the homework was, nope, want to know the p-value? It's between these. Yep, not good enough. But that's if you use the tables. This is one reason I don't like the p-value approach in general, because your table might be insufficient to nail down the p-value, and the best you can do is trap it between two values, which sometimes helps. But in the case of the F chart, it's a pain because you got to go from page to page and say, well, the F I'm looking for is between these. So the area is between these two significance levels up here. But I said that there were two ways to get the F value. One was with the tables. Does anybody remember the other? Yep. Or two, use technology to get the p-value. So how do we do that? Well, you can use a calculator or you can use Excel. I don't remember how to use Excel to get it, but I can figure it out in about 60 seconds. So you're about to see me refigure how to do something. All right, so let's open up Excel, and then I'm going to have to share it with the Zoom crowd so that they can see it. All right, share Excel. Now somewhere I've got this already figured out, but it'll be faster for me to refigure it out than to just go find that. Okay, I want to make sure that's large enough for everybody to see. All right, so I want you to, A1, I want you to tell me what something equals. Let's start by typing F and see what pops up. Oh, what's that say? And it's very small font size, so you may not be able to read it. Returns the left-tailed F probability distribution, degree of diversity, for two data sets. Left, I don't want left tail. Returns the right-tailed F probability distribution for two data sets. I think this is what I want. Let me select this. All right, what does it want? It wants X, it wants degrees of freedom 1, and it wants degrees of freedom 2. I'm going to assume that the X is whatever my F score is. And what was that? From the 6.00558? Okay, yeah, from the ANOVA table. Okay, and it wants the 2 degrees of freedom, which were 1 and 38. So is this the correct thing to ask Excel? Well, is that between 1% and 2.5%? So I'm going to say that it's the correct command. And again, I literally did not know what the command was, but I know enough about Excel to just start typing something, look at something and say, I think it's the right thing. So I'm going to go into the notes and write what you would type in Excel to get the p-value. I'm going to type exactly what you see there. In fact, I'm going to highlight this, copy it so that I can paste it into the whiteboard. So if you missed it, don't worry, it's about to show up again. Type this. The first number is the F from the ANOVA table, and the other two are the degrees of freedom. The 2 degrees of freedom. And maybe I should be more specific and say DF model and DF error. All right, so this presents a clear issue as a test question. How do you get this p-value? And the answer is, I wouldn't ask you on a test to calculate the p-value because it would require technology that I'm not going to force you to go buy. Can a calculator do this? Probably, if you know how to ask it properly, but I'm not going to require everybody to go out and purchase a certain calculator just because it can do this. If we need it, you get on Excel and you type in that command. As UT students, do y'all have access to Microsoft Office for free? Okay. Oh, wait a second. How do y'all access it? Oh, so you just get to download it? Okay, well, that's cool. Just showed up. Well, that's pretty cool. Just showed up there one day. Let me check something for you guys. 1 second. And I know this is way after the fact, but I want to see something real quick because I'm going behind the scenes here for a second. Navigation. Thank you. See, here's all the things I can put in Canvas and I don't. And I wonder if Microsoft Office is one of them. I don't see it. Google Drive, ProctorU, ProctorU. I don't see it because I know at TJC, one of the things I can make available to students is Microsoft Office. They can access it through Canvas, but apparently that's not the case here. Okay, but I'm assuming that, if you need to access Excel, then you can, or any other spreadsheet. Okay, so much for that. All right, let's go back to this. All right, we are here. So does anybody have any questions about, oh, I guess I should actually write the value. That would probably be useful. Oh, that blasted one away. P-value, not p-val. P-value was 0.18. I don't remember what it was. 517. Go back to Zoom, please. I'm just writing them down because that's what Excel told me. Wow. I'm not wow because you corrected me. I'm happy that you corrected me. I'm wow because I'm like, oh my gosh, I did that again. And why? If you don't know Control Z, you oughta. Control Z is the key command for undo. Oh, wait a second. I think it was 517 at this point. I really kind of don't care. All right. So from Excel, it tells us the p-value is that. So if you want to get a p-value for an F distribution, I highly recommend using technology. Man, that was a lot of work just to answer the p-value. I will not ask you to answer the p-value on a test. I'll just give you a p-value and ask you, what does it mean? Which is actually a really easy question. Where's my book? Sure. Like when I write a Canvas quiz for this, I would, and I would even put in the question reminder, here's how you get the p-value using Excel. If I ask you that. If I ask you, it would only be on a quiz, it would not be on a test. All right, I don't know if there's anything else to say about completing the ANOVA table. It's really a pretty quick task, except for this guy over here. All right, so any other questions about completing the ANOVA table, except for this guy over here? Okay, p-value approach. All right, I think we're getting into words now. Oh, here comes all the word problems. Ooh, look at all these words. All right. I'm not sure if there's anything I haven't shown you. Let me just scroll through here and see if there's any other task, because the rest of it is just putting in a context. But you know, we should probably look at a problem that looks intimidating. Let me see if I can find an intimidating. Oh, look at number 48. Oh, that's even. I should save it for y'all. No, we'll look at it. Okay. Points and penalty minutes in hockey. Anybody watch hockey? Yeah, I was going to say why. No, I tried watching. I just couldn't follow the puck, so I just the data set Ottawa Senators contains information on the number of points and the number of penalty minutes for 24 Ottawa Senators NHL hockey players. Senators, that's an intimidating mascot. We're the Senators, or we're going to tax you. Computer output is shown for predicting the number of points from the number of penalty minutes. What I really want to focus on is the type of computer outputs that you'll see in some of these problems. There are 3 types of computer outputs that you will see. One is called the regression output, the information that allows you to build this regression equation. Now, in this particular problem, they gave you the regression equation. We can sort of predict the number of points that you're going to score based on the number of penalty minutes. Now, the slope of this line is negative 0.113. What do you think it means that the slope is negative relative to penalties and points? Yep, the more penalty minutes you have, the less you'll score, which makes sense because you're on the ice less, you know, if you play hockey. So it kind of makes sense that it's a negative slope, because when the penalty minutes go up, you expect your point score to go down. But when you're given regression output, remember the coefficient column represents the numbers that you use to build your regression equation. Just the top one is your intercept and the second one is your slope. And then all the other pieces in here, the standard error, well, that's the standard error if you're doing a hypothesis test, or a the other thing we do, confidence interval. For the slope, this would be your test statistic. This would be your p-value. But let's just look at this for a second. In regression output, the p-values are for testing whether or not the slope is 0. Okay, so let's talk this out for a second. If I was testing whether or not the slope was 0, what would the null hypothesis be? The slope is 0 or the slope isn't 0? Now be careful, I'm giving you something that can be turned into an equation. Slope beta is equals 0. So let me ask the question again. What hypothesis would say that the slope equals 0? The null hypothesis, it demands equality. So that last value, and this is worth typing, so let me switch over to the whiteboard for a second. And we'll just quickly talk about the 3 types of computer outputs. 3 types of computer outputs. Computer. Okay, 3 types of computer outputs. All right, number 1, regression output. This contains the following. All right, I'm just going to do bullet marks. That doesn't, I know that doesn't look like a bullet mark, but it's the best I can do. The intercept and slope for the, and I'm going to put in parentheses, sample regression equation. Okay, so it contains that. It also contains the standard error for testing or estimating population slope. And it also contains the test statistic for testing. I'm just going to type beta. I'll type it correctly. But remembering that beta is, I'm sorry, beta 1. I'm just going to write it. Give me a second. I'm going to write beta 1 equals beta 1 there. There you go. The test statistic for testing beta 1 is equal to 0. But it also contains, and that beta 1 is going to disappear just for a second. It also contains the p-value for testing, and it's going to say beta 1 equals 0 again. And I'm going to put a line break in here in case it runs over that other beta 1. The test statistic, the p-value for testing beta 1 is equal to 0. So if you see regression output, and the question is, can you conclude that the slope is equal to 0? It's over if you know where to look. I'm going to go back to the book just for a second. Let me erase the numbers you don't need to look at, or erase the highlights. That last p-value is the p-value for testing if the slope is equal to 0 or not. Of course, equal 0 is the null, not equal 0 is the alternative. So based on that p-value, what's your decision about the null hypothesis? Based on the p-value, do you reject or fail to reject? You fail to reject the null hypothesis. Remember, the p-value is the probability you saw what you saw if the null was correct. Well, there's a 49.4% chance we would have witnessed that if the null hypothesis was correct. It's 50-50. So yeah, that's not very strong evidence against the null. So we would fail to reject the null. So we would accept the null, which says that the slope is equal to 0. So let me put all this in context, because I think this is important for me to write down so that you have it. First, let me see which question we're talking about. This is number 48. Okay. Yes. All right. So for example, in 9.48, with the null hypothesis is beta is equal to 0. I'm going to do something. I'm going to move this over here. You know what? Come on. I'm going to go to the next page. Trust me, I know what I'm doing. There we go. And I'm going to draw the beta 1 in there. We have a p-value of 0. I think it was 495. Let me draw the beta. It's going to drive me crazy not seeing it there. Okay. Let's continue typing. So we failed to reject the null. This means we conclude, and I know I misspelled conclude. I'll fix it in a second because it'll drive me crazy. So you know it drives me crazy when I see it later and I'm like, I can't change it. We fail to reject, we conclude, and the fact that I didn't capitalize the word this, I'm just going to let that slide. We fail to reject the null. This means that we conclude beta 1 is equal to 0. But what does that mean? When the slope is 0, this means the explanatory variable fails to predict the response variable. And I think I drew this picture before, but what does it mean for a line slope to be 0? It's a horizontal line. So if we had a horizontal line, and I'm pretty sure I've drawn this picture for you before, but if we had penalty minutes and points, and the line predicting them is horizontal, then that means it doesn't matter what your penalty minutes are, you always get the same number of points, meaning that it is a bad predictor. It is an ineffective predictor for the response variable for the number of points. So that's why we test the slope is equal to 0, because if it is, you're a bad predictor. Stop trying to predict the number of points based on the penalty minutes. So according to this ANOVA table, you shouldn't use penalty minutes to try to predict the number of points, because we don't have enough evidence to conclude that the slope isn't 0. So we assume that it is. All right, we got a chat. All right. Question. I'm listening, Colton. And if you want to unmute your microphone, you can ask it.
Yes, sir. Can you explain why we rejected the null again? Or we failed to reject the null.
Explain why we failed to reject the null. Yes, the p-value is, and let me type this out. And I'm going to take the font size down a couple of notches. The p-value is the probability we observed our sample if the null hypothesis was true. If the p-value is too small, less than 5%, this means we shouldn't, well, it's not that we shouldn't, but it was unlikely. We shouldn't have seen what we saw if the null was true. So we reject the null. However, if the p-value is large, like 49.5%, then witnessing the sample was not unusual. It doesn't contradict the null, the knuckle. It doesn't contradict the null. So intuitively, Colton, if your null is right, then the p-value is the chance that you saw what you saw. And if the chance of you seeing something was 50-50, that's not that unusual. It's like flipping a coin. So we have no reason to reject the null. But when your p-value is really small, like 1%, well, if the null was right, then there was a 1% chance we would have seen what we saw. That's highly unusual. And when we do that, and maybe this will answer your question a little bit better, Colton, when we do that, what we're really saying is the reason we saw what we saw isn't just because of the particular sample. Samples deviate from populations. That's just the nature of sampling. It deviated too much from the population claim, the null hypothesis, to assume that we blame the discrepancy, on the sample that we chose. So we have to blame it on something else, and we blame it on the fact that our claim about the null hypothesis, or our claim about the population, the null hypothesis, was wrong to begin with. It takes a little while for that to sink in. And I'll be honest, first time I taught this class 14 years ago, I didn't even understand what I was saying. So I stopped teaching the p-value after I talked to my boss and said, is it okay if I just focus on the critical value approach? But I understand when it's not always 100% clear about what the p-value represents. I hope that kind of answered your question. If it didn't, then I'll try to think of a better way to type it up later. All right. We've only got about, 12 minutes left. So let's just see what other loose ends I want to tie off. And by the way, I have no plans of starting 9.3 today. I don't know if you figured that out yet. But no, we're just wrapping up 9.2. All right, so I'm going to zoom back out and let's just look at the questions that are asked and talk about them. This is still about the Ottawa Senators and penalty minutes and points. Write down the equation of the least squares line. Wait, the what? When we reviewed this, I told you that there were 3 phrases for the same thing: regression equation, line of best fit, least squares line. So when they ask you for the equation of the least squares line, it's just the line of best fit. Wait a second. You want the regression equation? Okay. Now I'll tell you right now, on your test, I will not give you that last thing that I highlighted. I will give you this and ask you to write the regression equation. So you have to know that these 2 numbers are the ones that you use to build the regression equation. So that's what that's really getting at. It's kind of silly that they gave you the answer at the top, but you know what? I've seen sillier things. And use it to predict the number of points for a player with 20 penalty minutes and for a player with 150 penalty minutes, excuse me. So let's just talk about that real quick. If I gave you this equation, which I'm going to re-highlight, and asked you, all right, predict the number of points for somebody who gets 20 penalty minutes, what do you do? Yeah, put 20 in there and do the math. I don't know what it's going to equal, but I'm sure Miss Takus will tell us in a moment. About 27 points. 27 points for, wait a minute, that's not a game. Number of points Well, yeah, but hey, hockey player, how many points you scored? 27. You know how many hockey players have scored 27 points in a game? None, at least not at the professional level. So maybe it's for the season. Maybe that's what it is for the season. And I guess accruing 20 penalty minutes in one game is also unfeasible. Hey, sit out for 20 minutes. Like suspend you. So maybe this is talking about the whole season. I don't know. I'm not really a hockey fan. Okay. Interpret the slope of the regression equation in context. All right, well, let's just talk about that real quick. The slope was right here. I'll highlight it. Do you know what that means in terms of penalty minutes and points? For every penalty minute you accumulate, what do we predict? So if penalty minutes goes up by 1 minute, so for every extra minute of penalty you get, what does that mean about the number of points we expect you to score? Yeah, we expect your points to go down by 0.113. Now I know you can't score 0.113 points, so it's an on average thing. So on average, if we looked at everybody who went up 1 minute, then in penalty minutes, we would average out that and expect that their average decrease in points scored would be 0.113. And we don't have to say negative because we said the word decreased. So just remember that the slope is a comparison of rates. When one thing goes up, the other one does something else. So we always say we predict when the explanatory variable goes up by 1, then the response variable will change by that much. Okay. It's a rise over run thing. Give the hypothesis, blah, 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 blah. Give the hypothesis. Oh, hold up. C and D look the same. You see the difference between C and D? Yes, but what is it we're testing? What are we testing in C to determine the t-test of the slope? So we're testing the slope of the line. And in C, blah, 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 to determine whether the regression model is effective. So we're actually being asked 2 different things. Test whether or not the slope is 0. We just did that a minute ago. Because the p-value was too big, we failed to reject the null hypothesis and concluded that the slope was 0. But in D, we're testing the whole model to see whether it's effective. So we would have to look in the ANOVA table and look, hey, look at that p-value. Where have we seen that before? You think it's a coincidence? It's not. So really, we're saying the same thing 2 different ways. I think so. It's almost an exercise in redundancy, but it's answering 2 different questions. Now, when we get to chapter 10 and have multiple regressions, then there will be some discrepancies in there, and we'll have to talk about what that means. Gee, I wonder what % of variability in the points scored can be attributed to penalty minutes. Let me say the question again. I wonder what % of variability in the points scored can be attributed to penalty minutes. That's what R squared answers. R squared answers the question, what % of variability in you can I blame on that? Oh, it's only 2.15%. Well, that makes sense because we rejected the null hypothesis here and concluded that the slope was 0, aka bad predictor. And here we said reject the null hypothesis, model is ineffective. So it's all consistent. We're saying the same thing multiple times over and over again. Statisticians like doing that. I'm sorry, failed to reject the null. Thank you. Good catch. Good catch. All right, but they're all saying the same thing. Quit using penalty minutes. Oh, how did the 2 p-values compare? Well, they were the same. Interpret R squared. We just did that. Okay, so we just did that problem. So when you see it on a quiz, nobody should miss it. Okay. I think I've said everything I want to say for this. I wanted to try to wrap up a little bit early because there's a math contest going on over at TJC, and I said I would help, and I can't because I'm here. But I'm really wrapping up because I'm done. All right, so I am going to put together a homework assignment. If you want to hang around and watch me write it down, that's fine, or you can just catch it in an announcement. If you have any other questions, of course, you can hang around as well. Oh, how did I get all the way up there? And anybody on Zoom, if you have any questions, feel free to jump in. Otherwise, you're good to go. I will be saving the PDF of the whiteboards. Oh, we forgot to do that. I knew we would. Bring it up next time. Okay, here we are. I know. Let me figure out the homework question, and I want to keep the recording going till I record the homework questions. So we're going to do this, 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 that. We'll do this one. It'll be an easy question. We'll do that one because it's got a lot of parts to it, and then we'll do the one about the where'd it go? Is it 48? That's the one. Okay, so let me write this in the Zoom, and then I'll end the Zoom session. Okay. All right. Homework is going to be on page, I didn't even see what page it was. Let me type the questions first. It's a 30 through 44 even, and 48, but I need to go grab the page number. So give me 1 second to do that. This homework starts on page 598. Okay, page 598. All right, so there's the homework assignment. Okay, everybody got it? Well, I don't know if you write anything. All right, time to shut all this down. Let me make sure this saves as a PDF. Okay, open up that folder, and we will end the recording now.